consider the ordinary operation of addition of two real numbers. When you add two real numbers, you get another real number. Note that there are two numbers involved and they are giving you via the operation of addition another real number. And this leads to the idea of binary operations. Binary means 2. This is the formal definition of a binary operation. Let A be a non-empty set. A binary operation on A, on the set A, is a function of this type. Say the function name is f, its domain is the Cartesian product of A with itself and codomain is A. If we find such a function f, then f will be called a binary operation on A. But more commonly, instead of using letters to denote binary operation, although they are functions, we use some symbols to denote binary operations. For example, star. There are other symbols also. You will realize now why this is done. If star is a binary operation on A, then it's just a function of this type. And it continues a bit more next with this notational remark. If you have any two elements A and B in A, then you can consider the ordered pair A, B formed by them, which will be an element of this Cartesian product. And you can consider the star image of that element, because star is the function with A times A as its domain. So this makes sense, and it will be an element in A, because that's what star does. It takes an input from here, which is an ordered pair of elements of A, and gives an element of A as the corresponding output. So this is that output where the input is A, B. Now we don't normally use this notation because it has some unnecessary things. Things can be simplified like this. Instead of writing the image like this, we normally write, or more commonly write, A star B. Considering the source of that definition, the first example is natural because it's just the addition of real numbers. The ordinary addition of real numbers is a binary operation on the set of real numbers, which is just this function. So here itself you note that we use a symbol instead of using a letter. Although if you want, you can use a letter, say you can write A here. A stands for addition, but we don't do that. We use this well-known symbol, and although it's actually a function from R times R into R. Why is that so? That is because you take two real numbers in some order, although order does not matter, but those things come afterwards. You take say 2 and 3 and you consider the ordered pair 2, 3. Applying the function addition on that ordered pair produces 5. Or for example, the plus image of this ordered pair 4, 5 is 9, is the real number 9. But a much simpler notation is this: 4 plus 5 is equal to 9. Following this simpler notation. Similarly, multiplication and subtraction are also binary operations on R. You can take two real numbers and multiply them. That will give you another real number. Or you can subtract one real number from another one. So again you get a real number. By the way, why is this a function actually? You should also note that fact. For a function or for a relation to be a function, each element in the domain should have an image in the codomain. That is the first condition, and the second condition is that that image needs to be unique. For any two real numbers, we have a sum, which is also a real number, and we have only one sum. That is why this is a legitimate function, and that's why it's a binary operation on R. Similarly, multiplication and subtraction also are two legitimate functions. on R. On R means on R times R, but they are binary operations on R. However, division is not a binary operation on R. So we write here, however, division is not a binary operation on R. And the reason is that when you consider division as a function like this, then it's actually not a function. Or you can write, this function is not well defined. And the reason is this: you cannot divide by 0. Or interpreted in this setup, inputs like this do not have any output. Those inputs which have their second coordinates equal to 0, they do not have any output. But for it to be a function, every input needs to have an output, and that output needs to be unique. But such inputs do not actually have any output. So there itself it fails to be a function. So division is not a binary operation on R, but there is something else. But division is a binary operation on the set of all non-zero real numbers. Instead of this, if you consider this function, where now the set in question is the set of non-zero real numbers, not all real numbers, then this becomes a well-defined function. You see why, you can obviously understand why. If you take two non-zero real numbers, then this problem is no longer there. You can divide any non-zero real number by another non-zero real number, and the result will be a unique non-zero real number. So this time this is a legitimate function, and that's why division, in spite of not being a binary operation on R, is a binary operation on R difference 0. If we play with the possibilities a bit more, we see that division by 0 is not the only problem, because subtraction and division turn out to not be binary operations on the set of natural numbers. That means positive integers, where there anyway is no 0. Because of this, 1 and 2 are both natural numbers, but 1 minus 2 is not a natural number. 1 divided by 2 is also not a natural number. So when considered as functions from the Cartesian product of n with itself into n, then these are not functions actually. That means they are not binary operations on n. However, the first one is a binary operation on R, and the second one is a binary operation on the set of non-zero real numbers. So not just the function, not just the rule, but the set on which it is being considered, that also affects the thing. It's not just the elementary arithmetic operations of addition, subtraction, multiplication and division that you can consider when talking about binary operations, but other functions also exist which are binary operations. For example, you consider this function star, again from R times R into R, given by this formula. A star B means star of A comma B, that is A plus 4B squared. This is a legitimate function of this type. That is because for any two given real numbers A and B, A plus 4B squared is a unique real number. So that means this is a legitimate function, and that's why it's a binary operation on R. And the set involved need not even have numbers in it as its elements. Consider a set X, which may have any type of elements. But this is not the set that we are going to consider. We will consider P, which consists of all the subsets of X. You already know what this P is. It has a name also. It's the power set of X. Now you think of the operation of union of sets as a function with domain P times P and codomain P. Does it make sense? Don't get confused just by seeing this, okay? Let's see the individual parts. What does this mean? It means that this is a function which is supposed to take an input from the set P times P and produce an output which will belong to P. If you take an input from P times P, what will it be? It will be an ordered pair. where what are the first and second coordinates? The coordinates are elements in P. P is the power set of x, so that means these coordinates are subsets of x. Basically that means they are sets. So applying the union function on that ordered pair, say the ordered pair is a comma b. Applying the union function on a comma b means taking the union of the sets a and b. Will that produce an element in P? What are a and b? A and b are coming from P after all. So that means they are subsets of x. So if a and b are subsets of x, then their union is also a subset of x from properties of subsets. And it's a unique subset of x for those given a and b. That makes union a legitimate function of this type. The same can be said about the operation of intersection. So that is why union and intersection are binary operations on P, where P is the power set of some set x. Next we have these less common binary operations on R. This function, you can call it V because it looks like V, and you can call this one wedge. Okay, so they are also functions, each one of them is a function from R times R into R, and their definitions are this. The V value of a comma b, a and b are real numbers of course, is the maximum between a and b. That's the definition. Similarly, the wedge of a comma b is the minimum of a and b. So if we are given two real numbers a and b, obviously there is precisely one maximum and also there is precisely one minimum between them. So that's why these two functions are also well defined, and that makes them legitimate binary operations on R. It's not necessary to consider the V function or the maximum function, whatever you want to call it, on the entire set of real numbers, but say on this three element set consisting of 1, 2 and 3. It is still a binary operation on that set. And when the set involved is a fairly small one like this one, well, not exactly 3 or 2, I mean not having that many elements, but say 100 or thousands of elements as opposed to an infinite set like R, then we can sometimes describe, I mean this is the common thing, this is what we do in such situations. We can describe the binary operation using a table like this, and these tables are called composition tables or operation tables or Cayley tables. Okay, you will become familiar with this name later on. So let's see what this table has. You can already see, of course, because it's a table, it has rows and columns. The rows, the first row and first column, they have the elements. Okay, 1, 2, 3, 1, 2, 3. And the other cells are showing what the function V is doing to the ordered pairs. For example, this cell corresponds to the ordered pair 1, 1, 1, 1. Okay. What does V do to 1, 1? It gives us the maximum of 1 and 1, which is just 1. So that's why we have written 1 here. In that sense, the maximum of 1 and 2 is 2. The maximum of 1 and 3 is 3. The maximum of 2 and 1 is 2. The max of 2 and 2 is 2. Max value of 2 and 3 is 3. Similarly, these are all 3. So that is your Cayley table. Next, we note a difference between the addition operation and subtraction operation, a difference in their properties. The addition operation has this curious property that it does not matter in what order you add two numbers, the end result is same. It is not so curious because you have used these properties so many times that it has become natural to you. 2 plus 3 and 3 plus 2 are both equal to 5. However, The subtraction operation does not have this property. So this leads us to a notion, the notion of commutativity, and that is given by this definition. Let star be a binary operation on the set A. On A means A is a non-empty set, that's understood. Then we say that star is commutative if A star B is equal to B star A for all A and B in A. That means if you apply the function star on the two ordered pairs A comma B and B comma A, then you will always get the same result no matter what the elements A and B are. If that happens, then we say that star is a commutative binary operation. This means that addition of real numbers is commutative, but subtraction of real numbers is not commutative. A less common example of a binary operation on R that is not commutative is this. A star B is A plus 2B. For two given real numbers A and B, obviously A plus 2B is a unique real number. So this star is also a binary operation, but it's not commutative, because 1 star 0 and 0 star 1 are not the same real number. What is 1 star 0? 1 star 0 is 1. However, 0 star 1 is 2. So you suddenly realize that this property of addition, and which is also shared by multiplication, has become so natural to you that whenever you think of operating on two objects to get a third object, you expect to have it. You expect to have commutativity. However, if you just consider arbitrary binary operations, then obviously it's more likely that almost all of them will not be commutative, will be non-commutative. There are some other things also in this section that we will see in the next video on this topic. But a question arises. Why are we putting so much emphasis on functions of this type, giving them a name, binary operations? It seems as if we are just simply going on making pretty definitions and then seeing some examples, non-examples. Are we just simply playing mathematical games? No, the thing is that these functions arise in some systems which are studied in higher algebra. Those systems have been extensively studied and their theories have become very deep, and they have applications outside of mathematics as well. In fact, even in particle physics. So these are not just merely mathematical games of considering these things. Just suddenly we are saying that this will be called a commutative binary operation. Oh, that looks very pretty. It's not because of that. There are serious applications of these things, not just in physics but in other disciplines as well. That is why they have been considered like this. They have been given separate names, and it really goes very deep. You cannot imagine how deep these things go ultimately. This is how higher algebra starts.